lecture 11th for the course of machine learning, and what we are studying is different techniques to optimize deep learning models. What we have studied so far is we need to have a good initialization. So what we studied was greedy layer-wise optimization, where we have the unsupervised pre-training part, and then we have fine-tuning using the trained model using a supervised learning approach. To give us a good starting point for training our deep learning model, and then we studied the effectiveness of choosing the right activation function. In which we studied the efficacy of ReLU optimization activation function, and then the leaky ReLU version. And now we are studying how we can address the problem of overfitting in our deep learning models. And the topic that we are going to discuss today is dropout. So what is dropout? First, we will study the regularization. Regularization is a form of regression. That constrains or regularizes or shrinks the coefficient estimation towards 0. So what we are trying to do is we are trying to address the noise within our data set such that it does not affect the training part, and we are trying to limit its effect on the training of the model. In other words, regularization technique discourages learning a more complex or flexible model and why do we do it? So that our model can avoid overfitting. So what was regression? We know it is represented in this format. This is your multivariable regression equation, where your W's are basically your predictor variables, and your Y is your predicted variable. And the loss function can represent it in this format. Your loss function can be represented in this format. So we are considering the squared error. The target is to minimize the loss. So in regression, what we do is regularization. What we do is we try to avoid the model to learn the noise in the data. So we already discussed this before. If there is noise in your training data, so the model will learn the parameters involving the noise also, then the estimated coefficient won't generalize well to the future data. So this is where your regularization comes in hand, and it shrinks or regularizes the learned estimates to 0. So those estimates that are trained because of the noise, they are reduced to 0, so that they don't have an effect on the training of your model. And we add a penalty term to this squared error function. So we are going to add a penalty term, and the target of adding this penalty term is to avoid training the noise in the data, or penalize those values that will cause the overfitting of our model. Why we want to avoid overfitting? Because the overfit model will not be able to accurately generalize the model, and your model performance will be bad on unseen data. So we are going to include some additional information to prevent overfitting, and some of the existing approaches are early stopping, max norm constraint, weight decay, dropout, drop connect, and stochastic pooling. We will discuss some of them in this lecture. So what is early stopping in machine learning? So what we are trying to do is we are trying to stop the learning before converging too much. Hard to determine the time to stop. So how do we determine when to stop training the model? Usually determined by validation data set. As I discussed before, we divided our data into training, validation, and test data. So first we train the model, then we validate it, and when the training is complete, we test the model. So we check the performance of our training for our validation data set and see the model accuracy or model performance. So if the performance is good on training data as well as your validation data, then we can say that our performance, the model is trained well. But if the model performance of our training data is very good, but on validation data set the model performance is not that good, that means we may be having an overfitting problem. So one way of doing the early stopping is to check your error or your accuracies or model performances or your loss that we call. If it remains the same for 20 epochs or something, then we stop training the model and we update the weight. So we can determine how many values or how many epochs does the model train with the same values. If there is no improvement in your error or loss function or no improvement in your accuracy and validation accuracy for certain number of epochs, we say we stop learning the model and update the weight. We may update the weight again and then start training again. Another way is like max norm constraints, enforcing the weight vectors not to grow over given constant c. So a given value constant c is given, so the weight vectors do not grow beyond that value, and if it grows above the value of c, we cut its length to c. So certain level of error that our model requires. So weight values we fix. We can fix the weight value, the error function also, to certain level. And if that performance is achieved, we stop the training. So what is L1 and L2 regularization? That is one of the popular techniques for addressing the overfitting problem in machine learning. So L1 regularization is basically least absolute shrinkage and selection operator. And what it actually does is, and we can also call it the less so regression. So whenever you come across the term lasso, that least absolute shrinkage and selector operator, it adds absolute value of magnitude. So it adds an absolute value of the magnitude of coefficients or the predictors as penalty term to the loss function. So this is your loss function, and then it adds a term, absolute weight values or predictor values or the coefficient values, as a penalty term. So this is your penalty term, and how much penalty or how much weight we are going to give to this term depends on your value of lambda, this lambda value. So if lambda is 0, then we will get your original loss function, so there is no difference, whereas very large value of lambda makes the coefficient 0, hence it will underfit. So a large value will make it underfit, and a very small value will make it, small value such as 0, it is the same as the original loss function. And then we have the L2 regularization. Your L2 regularization is basically, we call that, another name is ridge regression. And it adds a squared magnitude of the error, squared magnitude to the original error term as a penalty term to the loss function. Hence the highlighted part represents L2 regularization element. And what we can also write this in another format. So in this case, again, if lambda is 0, then you can get back your original loss function. However, if lambda is very large, then it will add too much weight to your absolute squared values, and it will lead to underfitting the model. So we have to choose this lambda value carefully, and we can represent this term again as If we are taking from n symbols, then we have j is 1 to p, xij, wj minus yi. So this is our original error, and what we are doing is we are adding a 1 to p and wj squared. So this is the same thing, wj squared. Let's write it neatly, sorry. One to p, here we are taking p, so the weight values we are simply taking the squared of the magnitudes, so we are taking the square values. Okay. So what is the key? And we can represent this with tilde e. We know that this is for the regularization, not the original loss function, but a new loss function which has a penalty term added to it. So we can see that this can also work well for feature selection when we have a large number of values, large number of features. And the key difference between these two techniques is that the lasso function, this regularization, shrinks the less important features coefficient to 0. So those features that are less important, they are shrink to 0, thus removing some features altogether. So we are going to omit some of the features altogether, and it works well for feature selection.